All right. So we were stuck with the question of why not directly optimize over edge labels. And maybe it's helpful if we go through all the cases systematically for such a tiny triangle. So if I'm calling the edges here, A. So I'm calling them A, B, and C. Maybe C had a different meaning. By the way, that was one of the questions in the break. The C was always a vector. Yeah? So C was a collection of all the labels for C1, C2, and so on. All right? But here we need labels. Okay, I'm calling them K, L, and M, the edges here. And let's look at all possible edge labelings. So we start with 0, 0, 0, 0, 0, 1. Okay, I've not followed the binary digits here for a reason. So the labeling 0, 0, 0 means don't cut any edge. Everybody is in a single big family, and that is okay. Cutting a single edge, as we have just seen, is not okay. So there is no node labeling that would correspond to this edge labeling. So these here are not okay. And then let's look at that candidate here. So this means cutting edge L, cutting edge M, but not cutting K. That would be a legal solution. Okay. And the others are just permutations. So these are also okay. And then finally we have 1, 1, 1 means we cut every edge. Each node ends up being by itself. It may not be the least frustrated solution, but in any case it's a legal solution. It is also okay. So I could summarize this here, number of clusters. Here was a single cluster. Here there were 2 clusters. Here there were 3 clusters. And well, these are just not valid at all. Okay. So you see that it looks like a combinatorial optimization problem, because amongst all the legal solutions, amongst all the okay solutions, we need to find out which one has the lowest energy. And it turns out that for graphs that are bigger than the triangle, that indeed we have this element of needing to try out everything. Yeah? So it's we can be more or less smart in solving that kind of hard problem, but ultimately we need to resort to brute force in general to find the very best solution here, or resort to approximations, of course. Now, so what we can say here is that we need to make a statement here and say that Z is element legal solutions. That would be one way of writing it, or another way would be writing it to say such that here this collection Z of all edge labelings gives legit clustering. Now, I don't know an optimization program where I could enter, this information. So there are industrial optimization softwares out there, but you can generally not, enter an English sentence like argmin wz such that, z is a legit clustering. Yeah? We need to bring this into a more mathematical form. Yes, please. Yeah. So if I cut an edge, the question is why are they not legit? If I cut this edge here, this is equivalent to saying, I'm going to label the nodes here. I'm going to call this node 1, node 2, and node 3. By cutting this edge, I state that 1 and 3 are not in the same cluster. By not cutting the edge 1, 2, I state that they're in the same cluster. By not cutting the edge 2, 3, I state that they're in the same cluster. And so I end up with a logical contradiction. Okay? Thank you. Good. So the thing written here in red, such that Z gives a legit clustering, we need to bring this into more mathematical language. And, well, given this table, do you have an idea on, or does it remind you of something, or can you think of some kind of constraints? I should maybe add that a typical form of an optimization problem is to cast a problem as a linear program. Linear program means that we want to minimize or maximize, let's say, over some variable Z. The objective should be linear in Z. So I've now summarized all these edge weights W in a single vector W. And then there is that type of constraint. So in a linear program, you see that we have a linear objective and we have linear constraints. So linear in the variable to be optimized over, linear in Z. And there are several canonical forms. So sometimes Z no less than 0 is added as an extra constraint, but we can subsume this in the linear constraints as I've written them here. So I'm telling you that there are programs out there which solve optimization problems of this kind. Z is what we're looking for. W we have from some oracle. This was another one of the questions in the break. Where do I get the W's from? Let me scroll back up here. We get the W's from training a machine learning method, for example, by presenting ground truth like in this shape, and then this regression method, let's say a neural network, has learned to make a prediction for each of these boundaries if it should be preserved or not, or in terms of the graph, if this edge should be cut or not. So if this here were ground truth, then the neural network would have been trained to say, don't cut, cut, don't cut, don't cut, cut, etc. So this is where we get the W's from. Or you use a random forest or whatever. Good. So the Z is wanted. The W we have given from some oracle. And now the question is, how can we write A and B, a matrix A and a vector B, such that we rule out these illegitimate labelings here? So as long as we talk about triangles, actually, we can think of all of that as needing to obey the triangle inequality. And you know that for 3 points, let's say these are points here, A, B, and C. The triangle inequality states that if they live in a Euclidean space here, the distance between A and B must be no more than the distance between A and C, and the distance between B and C. So this is for points in a Euclidean space. Does that already do the trick for us? So can we think of these edge labels, the cut indicators, can we think of them as distances? Yeah?
I think in general we need to test if C is an equivalence class of the whole space, right?
I don't understand the statement yet.
We need transitivity, right?
We need transitivity.
And I think this is equivalent to being an equivalence class of our original problem, right? And maybe there's some clever thing in linear algebra that I'm missing right now that does the trick. But I don't know.
If we assign the AD for at least one of the edges, so if we have at least one in the cont, so in KL or M, and we have on the left hand side one is smaller than 0 plus 0 for our assumption. So the edges that should cut should be AD, and the other one should be AC or BC.
Yes, so we can always choose a pivot edge. The word that I've been using here, pivot, it's spelled like this. It means the edge of current interest, let's say. And let's consider. Okay, maybe let's start with a legit case. Okay, here it doesn't matter which edge I make the pivot. 0. So what I get here is that 0 is no more than 0 plus 0, and this is satisfied. Yeah? So this is all good. Let's take this legit case here. I would find, no matter which one I make my pivot, I would get that 1 is no more than 1 plus 1 if I use this triangle inequality. This is also satisfied. This is fine. But now let's look at one of those here. So here it says ZM. If I make M here my pivot, should be no more than ZK plus ZL. And here we have that 1 is less than 0 plus 0. And well, this is false. Okay, so this is, I think, what you were saying. We have so if we make, in this line here, if we make ZM our pivot, then we have violated this inequality. So this one is violated. But if we choose one of the other edges as a pivot for the same partitioning here, so here we had 1 is less than 0 plus 0, and we said that's violated. But if on the other hand, let's say we make a k our pivot, zk less than zl plus zm, then I get that 0 is less than 1 plus 0, which is okay. Yeah, so in other words, out of the 3 possible triangle inequalities that I can write, 1 will be violated for this illegal configuration. So for a triangle, the triangle inequality or triangle inequalities determine the viable edge labelings. Is everybody happy with that statement? So, let me repeat. This table here summarizes all the different ways in which we could label edges. Some of these rows correspond to a legal edge labeling. Here, for example, we get a single cluster out, everybody is together. Down here, for example, we've cut all edges, so we get out 3 clusters, which is also legit. Then we have here this way of obtaining different ways of obtaining 2 clusters. They can be better or worse in terms of energy or frustration, but they're all legal. And then we have these ledge labelings which are not okay. And for a triangle graph, such as one we considered, these triangle inequalities, if they're satisfied, they tell us that the edge labeling is okay. And if one of the triangle inequalities is violated, then we know that the edge labeling is not okay. It's not a feasible solution. Maybe ask a question. Yeah.
How does that generalize to larger networks or smaller nodes?
So as long as our graph is complete, so each node is connected to every other, this is all we need. We only need all the possible triangle inequalities. When we have a graph that is not complete, then we will need so-called cycle inequalities, which I can write down later. Yeah? But you can always make a graph complete by introducing edges that have a weight 0, and then triangle inequalities will work for you.
Do you cut these edges or do you?
It doesn't matter. I mean, for the frustration, it does not matter. Yeah.
For determining whether the edge labeling is correct.
Okay. So the question was, what if I have a graph which is not complete? So let's say I have a graph consisting maybe of these 4 nodes, and I have 2 missing connections. This is not connected, and that one is not connected. And I was saying that these missing connections, we can always add them. And now the question was, when I now want to ascertain if a particular edge labeling, for example here, I label this edge 1 and 1, I cut it. I label this one here 0, means I don't cut it. The question was whether that is viable. Yeah? Then the optimization routine will also find a labeling for the remaining edges. And for this remaining edge here, it makes no contribution to the frustration because it has a weight of 0. So it does not matter. And for that edge here, the optimization routine would conclude that we need to cut it also to get out something which is overall a consistent labeling. Okay. All right. Go ahead.
Could we also say that cutting an edge or cutting edges is only legit if it increases the number of clusters?
So when so you say we start with a single cluster, one happy family, and then whenever we cut one edge, we have to possibly cut further edges such that we get one more cluster out. That is correct. And I think it's even, I think we can say precisely one more. Yeah. Mm-hmm.
Because this is also something from which we can see that the second cutting one edge is not okay.
Yeah. However, this notion of clusters, we want to optimize over edge labels. And the clusters are only implicit in the edge labels. So it would be nice for our optimization routine if we could express in terms of the edge labels if or not it is legal. Okay, so let me give you the optimization problem for bigger graphs. We would argmin over z, w transpose z, such that for all simple cycles I'm going to call them C. So what is a simple cycle? It means that we don't revisit nodes. So let's say a cycle that goes around twice around the same nodes, that would not be a simple cycle. So for all simple cycles in our graph, and then for all pivot edges E in my simple cycle C, I require that ZE, the edge cut indicator for this pivot edge, should be no more than ZF. Okay, so this is what we have on the right hand side is a sum over all edges in my current simple cycle. Except my pivot edge. Okay, and so this is something that we can now really translate into matrix A and vector B in this form that I've given up there. Good. Now, this actually works for clustering triangles. Unfortunately, or we need a little more. We need some more constraints. So, for example, we need a constraint that does not allow our cut indicators to become infinitely negative. Yeah? Otherwise, we could make the energy infinitely negative by sending some of the z's to minus infinity. Yeah? So, for sure, we need some box constraints, and unfortunately, it turns out that we even need integrality constraints. Why? Because otherwise we may get, as a result from our optimization routine, we may get edges which are a little bit cut. Yeah? So our optimization routine may tell us that the frustration is minimized by cutting edges a little bit. And we want to know, is the edge cut or not, but not is it cut a little bit. Yeah? And in terms of optimization, this last innocent looking line, that the edge indicators should be 0 or 1, this is the bad guy, and this is the guy that makes the optimization problem so hard. So if we look at this kind of optimization problem, the thing on top we call the objective, and the thing on the bottom, so everything that comes after such that, these are the constraints. And here, in fact, we have a linear objective, and we have linear constraints, except for the last one. This here, unfortunately, is a non-convex thing. So a linear objective is convex, linear constraints are convex, and unfortunately the last line is what makes the entire problem non-convex. And in optimization, this convexity or not decides whether your problem is a hard one or not. So let me make a small excursion of optimization, or let's do a small excursion here, hardness of optimization problems. I can have, on the one hand, and I'm going to make a sort of a graphical table for you here. We have the objective, which can be convex or non-convex, and we have the constraints, which can be convex or non-convex. And I'm going to make a table for you here, which you don't see in any textbook because it's very qualitative, but I hope that it will give you an idea. So let's say convex objective a parabola, for example, is convex. So let's say the objective I'm going to plot in green. A parabola, for example, would be a convex objective. It doesn't have to be an isotropic one. I could take one like that. And as a constraint, I'm going to draw these in red. Maybe my constraint set says that only this part here is legal and the rest is illegal, or feasible and unfeasible. So that would be one example, or actually a more typical set of constraints is to have linear constraints, where we would have a linear constraint that says legal and illegal. Maybe we have a second linear constraint which says legal and illegal, so that overall our feasible region is only this part here. And still we have, in this case, a convex objective and convex constraints. Or let me give you another special case. Let's make the objective linear also, as in linear programming. So the objective would measure the energy, like maybe the energy here is 0, 1, 2, 3, 4. So we want to, in terms of optimization, we want to go as far as we can in the top right corner, but we have these constraints in addition. And so our optimal solution in this particular case would be, for example, here. Now, when the objective is convex and the constraints are convex, the entire problem is easy. If, on the other hand, the objective is non-convex, so I'm inventing something here, something which has a few minima. Think of this as a topographic surface, yeah? And what you see here are distinct minima. No matter what the constraints are, we essentially end up with a enumeration problem. We need to visit all the minima and find out which one is deepest. And if we work in an optimization, if we don't optimize over 2 variables, but if we optimize over 1 million variables, or even just over 10 variables, finding all the local minima there is in fact hard. Where hard means NP hard. What if the objective is convex? Let's say, for example, a linear objective, but the constraints are non-convex. So, for example, my constraint set now looks like this, where on that side I'm legal and on that side I'm illegal. I again end up with an enumeration problem. I have here many local minima. This is a local minimum, this is a local minimum, this is a local one, this is a local one. And again, this makes for a hard problem. Well, and then if you have a non-convex objective and non-convex constraints, hard. This is very hard, okay? Doesn't get any worse. Good. This is end of pictorial excursion to optimization theory. And there are a few benevolent cases where a problem on closer inspection turns out to be simpler than you expected. Yeah, so there are some lucky problems that look like, for example, they have non-convex constraints, and then yet in the end they can be solved in closed form. But these are very rare cases. You had a question?
Yeah,
Okay. It means that we cannot verify the correctness of a solution in an algorithm which would scale polynomially with the size of the input. And in practice, what this means is, so when we talk about the complexity of algorithms, we care about if I make the problem twice as large, how does the amount of storage or the amount of compute that I need, how does it scale? Does it also multiply by 2, or does it scale, or does it... So if we call n the size, the question is, does it grow as n log n, or as n to the squared, or n to the cubed, or something? And in these NP-hard problems, the difficulty of solving them grows extremely fast with the problem size. So we can only hope to solve problems of modest size exactly. Yes?
And how do we see the complexity in this problem? Because it is has only discrete values allowed. And can this ever be convex?
Okay. The question was, how do we see the convexity in this problem? So this here, these are all linear constraints. So each single one of these lines, so if I pick a given simple cycle, the simple cycle defines which edges take part in it. I define a pivot edge. Then what I get here is this linear constraint is essentially half space. Yeah, so in the space that I optimize over, this means that it defines a surface. So the surface here would be ZE equals sum over ZF F element C without E. That would be the surface. But now we say ZE has to be less than that. So we say that this area up here is illegal, and that is legal. That would be for just one of the constraints. But now we have many, because we have many pivot edges, and we might have many simple cycles. So maybe I get another constraint, which also has a legal and an illegal side. And I might have more constraints. And such a collection of half planes, if I intersect them, the intersection can either be a finite set like this, or it can be the empty set, the feasible region, or it can be, the feasible region can also be open-ended, it can be infinite, but it always has the shape, what is called a polytope, which is a convex body. So this is why these first constraints here are convex. However, this thing here, if we now say we don't permit all values, but we only permit integral coordinates, like so, let's say these are the integral coordinates, then I am reduced to an enumeration problem.
And can I ever have a convex problem with only discrete values allowed?
Can I ever have a convex problem?
And the last constraint only gives us discrete values exactly.
Mm-hmm.
Can this ever be a convex problem?
No.
So basically, if I see this, I already know it.
Yes, when you see this last line, then, well, the thing is that sometimes, if we only take the previous constraints, sometimes we're lucky and we already get an integral solution out. And then I was lucky using only convex techniques. I know that I have found a globally optimal solution. But if with the former constraints I get a fractional, then I need to enforce this integrality constraint in addition, and then I know that I'm in trouble.
So it's very, very unlikely if I have a discrete thing that it is convex in the end.
It depends. It depends. So it depends on what my... Where am I? It depends on in which direction W points. It could be that a W points in a direction such that my optimal solution lies in a corner of this polytope, and this corner is already integral, and then I'm good. But there are other corners which are not integral, and then I'm bad. Yes?
The last line, so the last construction, actually the Z is this set of 0, 1.
Yes, thank you. So, so ZE should be 0, 1. I'm just going to write it like this for all edges in the edge set. Yes?
So an empty problem should be, you should be able to check it in polynomial time, right? But the only way to check this, I see on the first try, is to go through it and check for every single one. That's the way we also find the right solution. So there's always a clear way to check a solution, which is just computed again. But in an empty problem, there needs to be an easier way to check a solution than to compute it. So how does that work here?
How checking the solution here works?
Yeah.
By running connected components, which is something that can be done efficiently, and then asking if on any uncut edge I find the same label, essentially. Yeah? So that's one way. Another way is to verify all of the cycle inequalities and check in addition if the solution is integral or not. And if the cycle inequalities are all satisfied, then you know you're good. No? Okay, so this class of optimization problems is, so linear programming is a really important class of optimization problems. And importantly for you, you can find ready-made solvers for linear programming. So what have we done? Let me scroll back. We have taken some reasonable, we have defined some reasonable frustration criterion, which was that if things that want to be together become separated, you have to pay a penalty. If things that want to be together are together, you get a reward. We have defined a frustration in terms of a node labeling. Then we have rewritten this in terms of an energy function which only depends on the edge labels. A bit further down, we have rewritten this in terms of something which only depends on edge labels, but when we go to edge labels, we no longer have this consistency of the solution guaranteed, and we need to enforce it explicitly, and we do enforce it by using the triangle inequality in a complete graph, or in an not complete graph, the so-called cycle inequalities. Yeah? The things here, these are called the cycle inequalities. And we now have massaged the problem into a form that an integer linear programming solver will ingest and give you a solution for. So you input the attractions and repulsions. You read from your graph, you need to find all the simple cycles, etc. And then you give it to the program and you get out edge cut indicators that give you your globally optimal clustering. Now, let me summarize what are the properties of this correlation clustering, or multicut, which is another name. What's good is that it finds the number of clusters automatically. So you do not need to input, I'm looking for 5 clusters or however many. It really comes up with itself with the optimal number of clusters if you solve this. And this can be a single cluster, or it can be each node by itself if the interactions are accordingly. What's bad is that it is computationally a hard problem. And you can solve this exactly only on instances which are not too frustrated. In the real world, you can use approximations that, for example, in these computer vision applications, we know work extremely well, because we can solve on modest-sized instances, we can solve the problem exactly using an integer linear programming solver. Then we can try out an approximation and compare. And such approximations, they will not work well for all graphs that you can invent, but they do happen to work well for the kind of graphs that we extract from computer vision applications.